this video is about the definition of congruence. What is congruence in geometry? I'm making this because I wasn't terribly satisfied with the videos I found online, and I'm doing this outside, so there might be some background noise occasionally, so bear with me. So first of all, congruence plays, I'm just reading what's on the screen here. Congruence plays the role in geometry that equality plays in arithmetic and algebra. And you're doing arithmetic, when you're doing algebra, you often say, these numbers are equal, or when you're doing algebra, you're putting down equal signs in equations, x squared plus 2x equals 8, and solving. And it's a way of saying that these things are the same. And congruence plays that role in geometry. We're going to see that it's a way of saying that figures are the same. In fact, the symbols are closely related. The symbol for equality, you know, it's just the equal sign like that. The symbol for congruence has the equal sign, but then we put a little tilde above it like that to show that it's not equal, it's congruent. It's really all not that important, but that's the tradition. So you'll be seeing a lot of this symbol. This is the symbol for congruence. So what is congruence? Well, the way we'll usually think about it, this is the informal, it's not the mathematically rigorous definition, but the way we will think about it in our heads all the time is congruent figures have the same shape and the same size. So here I have this odd polygon here. If I just make a copy of it and drag it over here so we can see it clearly, this is a congruent polygon. It has the same shape and the same size. It doesn't matter if I drag it around to another location, if translate it around, it's still congruent. It doesn't matter if I choose a center point and rotate it, like if I spin it around to here, these still have the same shape and the same size. The fact that one is rotated doesn't matter. It doesn't even matter if I make a mirror image of it, if I reflect it. If I put a mirror line down here and I take this and I reflect it, oops, sorry about that. If I reflect it to get this one down here, now we have three congruent figures. All of these have the same shape and the same size. It doesn't matter if it's rotated, it doesn't matter if it's translated, it doesn't matter if it is reflected. So that's the informal definition, and most of the time that's how we'll think about it. But I also wanted to introduce you to, although I'm not going to test you on it or anything like that, what's the formal definition? Like, how do mathematicians think of congruent figures? And so here's the formal definition. Two figures are congruent if there is a sequence of one or more reflections that places one of the figures right on top of the other. Now, mathematicians wouldn't say right on top. They would say something else, but that gets the point across. Let me show you what this means. You don't have to be able to do anything like this. I just wanted to demonstrate it to you. These quadrilaterals are congruent. They have the same shape and the same size. I want to show you that we can actually do a sequence of reflections that puts this one directly on top of that one. You don't have to be able to do this. Let me show you how it works though. First, I'm going to make a reflection that puts one point of one on top of the other. So this is going to be my mirror line, and I'm going to reflect this quadrilateral through that line like that. Hide this away. So there's my first reflection. You can already begin to see, if I look at this one compared to this one, that they look like mirror images of each other. And if I do just one more reflection, make the mirror line again, this will be the mirror line this time. If I reflect it, boom, it landed directly on top of this second one. So this and this quadrilateral satisfy this definition of congruence. There is a sequence of one or more reflections, this time it was two, that places one of the figures right on top of the other. By the way, this shows formally, which is obvious, that a figure is congruent to itself, because I could take any figure at all, reflect it through any line, oops, and then reflect it right back. That would be two reflections, and it lands right back on top of itself. And so that shows a figure is congruent to itself, which is obvious from our informal definition. A figure has the same shape and size as itself. So let's look at congruence in some simple cases. What about points and lines? First of all, 2 points are always congruent. They clearly have the same shape or same size, and it's pretty easy to see that there's a reflection. The reflection line would be around here. That would reflect this point directly onto this one. So I can always reflect one point onto another point. So 2 points are always congruent. Same with 2 lines. If I have 2 lines, there we go. It'll take a couple of reflections to show that I can reflect this line directly onto this one. It'll take one to put this point onto here, and then another one to line that point directly onto there. So you can show pretty easily that 2 lines are always congruent. And this makes sense based on the informal definition. 2 points, any 2 points anywhere have the same shape and same size, so all points are congruent. Any 2 lines have the same shape, they're lines, and the same size. They go forever. So they have the same shape and same size. The first non-trivial case where there actually can be non-congruent things are line segments. Line segments are pieces of lines that have endpoints. It's all the points between here and here. Are these 2 line segments congruent? Do they have the same shape and the same size? Well, they have the same shape. They're line segments, but one is longer than the other. This one is longer than this one. And so it's impossible to reflect this one and have it perfectly cover this one, because reflections preserve length. This will stay the same length as this. Or reflections of this will always be the same length. So there's no way I can cover this. So the only way for 2 line segments to be congruent is if they are the same length. So 2 line segments are congruent if they have the same length. So there's only one thing we need to measure about line segments to tell if they're congruent. I have to measure each one's length. If those are the same, they are congruent. If they are different, then they are not congruent. Another very simple figure is an angle. So here are angles. A brief word about measuring angles. The length of these lines has nothing to do with the measure of the angle. The measure of the angle is the amount of turn going from here to here. Now, these 2 look like they have the same number of degrees, the same amount of turn going from here to here. And I can actually ask Sketchpad, the piece of software I'm working in, to measure them for me. I'll measure this angle. It says this is 61.62 degrees. And I'll measure this angle. It's the same. So these 2 angles are congruent. And that is how we tell if 2 angles are congruent. 2 angles are congruent if they have the same number of degrees. Or what is sometimes called the same measure. The word measure is used for angles like the length is used for line segments. And that's this brief little video introducing congruence. The idea of congruence, that figures are the same shape and the same size. The first complicated case is triangles, and we're going to spend an entire unit looking at triangle congruence. That's what the next video is introducing you to. Thanks for listening.